Okay. So, the three factors that affect the force on the electron are the nuclear charge, the distance of the electron from the nucleus, and the shielding effect. So, the nuclear charge, this can kind of be estimated from our Coulomb law again, that we have this Q over R squared. I'm just going to use the proportional version so we don't think about the constant there. So as the nucleus gets bigger, then for one electron, we can think about that as being one electron being one of your Q's, and then the growing nucleus being the other Q. So if you have a proton, you've only got a +1. You put a fluorine, you got like a +7. You got a uranium, it's like 92, so there's 92 protons in uranium, so it would be like 1 and 92. That's one of the forces involved. So for any given electron, it's, you know, that electron must be really happy to see the nucleus of uranium. Of course, there are some other factors in here. We have, right out of that equation, we have the distance of the electron from the nucleus. So considering how far an electron is stuck being from that nucleus, that's going to have an effect. So according to Coulomb's law, further two charges are, the lower the attraction. That's of course again that R squared down there. This is actually the same formulation as gravity. Gravity follows the same rule, the same format. It's big G mm over R squared. So it's actually the same law, same model applies, but talking about electric charges this time. So of course, in some of these bigger, this is where the principal quantum number comes really important, right? Because the principal quantum number kind of controls where the electron is relative to the nucleus. Higher the principal quantum number, the bigger this R is, and then that's tanking that force. So the attraction, this attractive force, is going down. Even if there's like a really big nucleus, if the electrons are forced into an outer shell, by the other effects that we talked about, like Hund's rule and Aufbau, if those are forcing the electron to a higher shell, then the R squared value is going up, and so that's going to lower the effect. So this is where quantum effects, the quantum number, principal quantum number, is proportional. It's a proportionality symbol there to our distance. And then this is probably the last sort of interesting effect, which is the shielding effect. And I like this effect a lot because it explains why it kind of goes and why the shells kind of form, and why the shells and the properties kind of seem to repeat themselves. So shielding is the idea that if you can fill a shell, then that shell will sort of absorb these first two forces, and they will reduce the total effect of number one on the next electron. That's sort of the idea. So inner electrons tend to screen or shield the force of the nucleus from the outer electrons. So if you have, for example, a nucleus, and inside that nucleus we drop, let's drop 11 protons. So 11 protons, so that's a sodium. So we drop 11 protons into that nucleus, and then we start building out our shells of electrons, just like Bohr described. You know, here's our two electrons in that 1s orbital. This is our 1s, and we've got another 2 electrons in the 2s, or another 10 electrons, 8 electrons in the 2s and 2p orbitals, the secondary shell. Then we drop in our last shell, which is the 3s shell, and we put our 1 electron in there. There is an attraction, right? Because you have 11 protons, then 11 negative charges from the universe try to attract themselves to try to cancel that value out. But when we consider the forces between these electrons and these different shells, we can look at this this attraction here between this 1 electron and the 11 in the center. Coulomb's law starts to fall apart, and instead of doing something like, instead of taking the proportional as 11 times 1, so 11 positives and 1 negative, we actually these ones screen out the equivalent of 10 of those charges. So we lose, so the force gets dropped down to just 1 times 1. So that made no sense. I can see by the looks of your faces. You're like, so let me just try that again. I'm gonna do something different. Okay. One way, let's look at it this way. So these electrons in the center, in the 1s orbital, there's nothing in between that electron and the center. So for them, the force between these 2 electrons and these 11 electrons is that for any one of those electrons, it's like 1 negative charge compared to 11 positive charge. Very strong force, right? You're like 1 times 11 divided by r squared. It's also the smallest r squared, 1. Like quantum number 1. So super huge charge on that center nucleus. But when we go to consider the next shell, we actually have to take away whatever force that was here. Some of that force is essentially kind of taken away from the effect between the 8 electrons and the 11 electrons. So for every consecutive shell, the amount of force pulling them inwards is a little bit smaller than it should be. So this is like they look at it in this very this nice little diagram here, is that the idea is that this electron here, because it's closer and has this very strong interaction, it kind of casts a shadow. It reduces the force that's affecting this one. So it's not going to be just a straight up Coulomb force where you're like, we just need to know the charge of the 2 things and the distance. We can't just take that for granted. We have to actually incorporate that some energy's been sort of absorbed by those earlier electrons. So the attraction to these outer valence electrons is lower than it should be, or lower than it should be if there's nothing in between. Does that help? Please, yes. In the electrons in the shell? Well, this first one is this is quantum number 1, right? So we get only s orbitals. S orbital can have 2 electrons. Shell 2, we have s and p orbitals are possible, so we get 8 electrons. Shell 3, we would have another 2, and then there's a p orbital, and then there's a d orbital, but we haven't started putting. I'm only putting 1 electron for now because I only have 11 protons. So 2, 8, 11. So 2 10.
If you say 50.
If I put 50 protons here?
Yeah.
Oh, then I have to keep building shells and like.
So say sufficient is how many convert?
Yeah, so it's based on the quantum numbers and what's allowed. So we would have 3 allows for S, P, and D. So we could have up to 18 electrons in shell 3. Shell 4, S, P, D, and F. So we can get a whole bunch more. Yes.
First cell only has 2, so how come it blocks the other one that has more than it? The first one.
This one, yeah. So this little 2 electrons in the 1s, it takes a little bit of energy away from the next one. It's not a lot. They're only 2 electrons, right? So then the next one, instead of feeling the full force of 11, they're probably feeling more like a force of 10 maybe, or it's a small reduction in that force. Yes.
I was gonna say a good example would be
That's great.
a couple magnets, and then each time you put a piece of paper in between it, the force gets weaker.
Sure. Yeah. That's actually not too bad. Yeah, I like that actually a lot. I mean, I guess they are all magnets, but all the way up. But Yeah, it is it's similar to that. That if you're putting layers of something in between, and it reduces that force. The force is reduced by the distance as well. So you've got both a reduction by distance and a reduction by screening. So that's why when we get to something like a sodium or like a rubidium, right? Rubidium has this one electron way on the outside, and then there are 36 core electrons. And those 36 core electrons, even though it has this huge nucleus, the fact that that electron's way on the outside, that's its first hit against it. And then because it's also shielded by 36 electrons, the amount of force that's holding that one electron is very low. So very easy to remove it. And so that's where we're going to see, this is going to translate into ionization energy and radius. And that's going to be over here. So we'll start to talk about this a little later. So this is the idea of, this is how much energy it is to remove that first electron for sodium. So that's sodium. Look at that little tiny bit, right? So that gives you an idea of how much force the nucleus is actually exerting on that one electron. To remove the second electron, which is in the p orbital, much harder. You know, this is like almost 5,000 times harder, right? Like it's a jump in the thousands. So it's like thousands of times, or almost thousands of times harder. And then each one after that increases in difficulty, because as you remove electrons, you remove the shielding. You're working with like things that are in the same order. Yeah, and so we'll talk about this. Look at the pattern for magnesium. What do we notice about magnesium, and why? Can you explain that? Could you kind of hand wave that explanation? Think about magnesium here. Look at those first two energies to remove the first two electrons. Pretty easy. Why does that make sense?
We have the nucleus, so nucleus energy. When it goes far, we need high energy.
Yeah, as we're kind of digging down into the atom, as we're trying to rip stuff that's closer and closer to the nucleus, it gets harder and harder. That outer shell is all the way in the 1, 2, 3 in the 3s orbital, so it's actually like quite far away from the nucleus. So those have very little connection to the center. There's also 11 electrons in between. So there's a lot of shielding. So those outside electrons, very difficult. Then all the other electrons, they kind of go in a nice order, right? These are almost straight lines. So of course every one of them is harder to remove, but it is kind of like a straight line once you're in the same shell. This is all going to be 2, n equals 2. This one here, n equals 3. These two, n equals 3. These ones, n equals 2. Look at aluminum. You're just walking down the line, n equals 3, n equals 2. So the first shell, the outside shell, much easier to remove. A little harder every time you take an electron off, but still really easy to remove. And then n equals 2's. But then when you go to the next shell, it's hard. Yeah.
So if the orbital is not filled, so it is easy to remove, right?
Yeah, it's usually a little easier to if it's not full. Yeah, exactly. And so we can look at something like, you're talking about full orbitals. So look at the chlorine ones. Notice that it's a prohibitive amount of energy to even take one electron off. Or sorry, one electron. This is the first electron. Easy to remove the first electrons, and then as you get to chlorine and arsenic, very hard to remove those first electrons. 3 times harder to remove the electron for a chlorine. These are ionized, so this is not adding, this is removal. So, not that it's not impossible, but it's just not going to last for very long. Okay, with that, I've had enough. We got pretty close to the end of this. This might give you enough to finish this little worksheet. We'll review this last lesson on Monday. Next Friday is the test. I'm aiming for essentially this, but probably in a format you can actually fit your answers in a little better. this is for practice. I probably won't go through the answers for this, but I would encourage you to find a partner to go through them with, or to book time with me after class, or to ask me questions about it, or come before, or ask me questions of if you're having trouble with the problem, and then we can also do a review on it. But this will be essentially a test for Friday. So if anybody needs another copy of that, then come see me. Electron configuration hand-in. I probably have more of those. Did I give you B yet? Did I give you guys B for hand-in? B? That was off-bow poly exclusion and Hun's rule. So, nope. Oh, there they are. They're in my hand. Okay, so there's something to keep you busy as well. You gave that to me on Monday. And yes, please grab one. Anybody else? Have yourselves a great weekend. Stay focused, stay engaged with the material if you can. And I look forward to seeing you on Monday. This has been a great week for attendance. I mean, I hope you're not just showing up for the draw. Oh, the draw! You guys got your tickets. Yeah. If anybody didn't get the test, there it is. Tickets. I'll catch you on the way out. There we go. Thanks for having us. Thanks, Emily. You feel better. I don't think I gave out a. Oh, did I give out a? I did give an electron configuration worksheet. Oh, did you get that one? That's like practice problems and stuff on it. Cheat sheet for Friday. I'll include formulas like on a sheet. Yeah. Okay, I'll get you one more. I got another one.
Have you seen the Tesla coil?
Oh, you
Tesla
have to
coil. It was right.
In the box over there.
I had it
The big
with
white
the
beaker.
Oh my god, I don't
with the thing. It was like right here. I used it.
that, but
And that was a while ago.
That was a while ago.
And I
Yeah.
put it away and I put it right there.
Yeah, you need to have like
On
two
the box, right?
connecting and then
Yeah.
Let's
that
see it.
connecting to that
Yeah.
connecting to.
yeah, I connected already, but I have to do it big paper, yeah?
Yeah. Maybe ask the future
There
next
is
door.
one.
Yeah.